discussing numerical integration, and so far we have talked about trapezoidal rule and Simpsons 1/3 rule. Simpsons 1/3 rule is usually more accurate than trapezoidal rule. However, it has certain restrictions. It requires even number of intervals to implement, which we may not have always. Here in this lecture, we'll talk about Simpsons 3/8 rule, which is also as accurate as Simpsons 1/3, but it requires an interval that would be multiple of 3. Together, we can manage even odd or even number of interval, and we'll see that in this lecture. Also, we'll discuss how this 3/8 rule exactly is derived. Derivation is same as Simpsons 1/3 rule, but we didn't discuss the derivation in Simpsons 1/3 rule. We'll discuss it here, and then you will understand how to do it in Simpsons 1/3 rule as well, because the derivation in Simpsons 1/3 rule will be easier than the derivation in the 3/8 rule. So let us see what is Simpsons 3/8 rule. Let us first recall the Simpsons 1/3 rule for 3 points. So here we have these 3 points, these red dots, which is connecting over this blue line. The blue line is my actual function, and Simpsons 1/3 rule approximates it with this red line. It interpolates a polynomial through these 3 points. Trapezoidal rule connects a straight line between 2 points. So this is also an interpolation, but this is only a linear interpolation. Trapezoidal rule requires 2 points. Simpsons rule requires 3 points. So here, based on these 3 points, at x0 I have the value of function y0, x1 I have the value of function y1, and x2 I have the value of function y2. Simpsons rule gives us the integration of y between x0 to x2 equals h by 3 y0 plus 4 times y1 plus y2. Now, in a curve where the area we are trying to evaluate is large, or the integral is large in x0 to x2, that is large, then we take this as composite Simpsons 1/3 rule, and we take the integral between x0 to xn. We have this composite rule of h by 3 y0 plus 4y1 plus 2y2, etc., etc., up to 4yn minus 1 plus yn. So it will go 4, 2, 4, 2, 4, 2, etc., and at the end it will be 4 and 1. This is how the coefficients will go. Coefficient starts from 1, then it goes from 4 to 4 to etc. So to implement this, we need this 2 interval at least, and again after this segment, in next segment again I need 2 intervals. So 1, 2, 3 points, then 3, 4, 5 points, then 5, 6, 7 points, etc., etc. So we always need odd number of points to implement Simpsons 1/3 rule. Odd number of points mean even number of intervals. So we always need even number of intervals to implement Simpsons 1/3 rule. Simpsons 1/3 rule is a very accurate implementation. It is locally 5th order accurate. Locally means when I am implementing only in one segment, that is 5th order accurate. But globally, which means when I am taking many such segments together, the accuracy, the errors will add up and it will become 4th order accurate. So it's a highly accurate scheme. It's much more accurate than the trapezoidal. But then the problem here, as we are talking about, that n must be a multiple of 2. N means the number of divisions here, number of intervals here. These are n's. So the n equals 1, n equals 2. We need multiple of 2. N is the number of interval, and n plus 1 are the number of points we are taking So number of points has to be odd, or we can say number of intervals should be even. Now, this is a restriction. We cannot have that all the time. Trapezoidal rule, of course, does not have such restriction. The intervals could be even or odd. We can still use trapezoidal rule. That's the good thing about trapezoidal, but it is usually less accurate as compared to Simpsons rule. So now, if we have odd interval, we have to revert back to trapezoidal. We can have in a given domain, we can have some part using Simpson and some part using trapezoidal. That is possible. But then eventually, when we have odd number of intervals, at least some part has to be trapezoidal. So, for example, here this n has to be a multiple of 2 in Simpsons rule. So let us say we have n equals 7. So it is not a multiple of 2. We can directly apply trapezoidal here. Here 1, 2, 3, 4, 5. And let us say this is 6, 7. This is my complete domain. I can directly use trapezoidal, or I can go by Simpson. First 2 is fine. This is 2. This is 2. This is 2. Up to this we can use Simpson, but here last 2 points I have to use trapezoidal. So it could be a combination of Simpsons plus trapezoidal. But as soon as I use trapezoidal, the overall accuracy of the calculation will reduce, because the overall order of accuracy of calculation is same as the least order of accuracy of calculation for the scheme that I am using, which means that the order of accuracy of this Simpsons plus trapezoidal will be same as the order of accuracy of the trapezoidal itself, because the order of accuracy of trapezoidal is less than that of Simpson. So how we can avoid such situation, or the idea is that how we can take care of odd intervals and we can keep same accuracy as Simpsons 1/3. That is where the Simpsons 3/8 rule is coming into picture. Simpsons 3/8 rule is as accurate as 1/3. However, here n needs to be multiple of 3. Of course, how we'll take care of that, we'll take a look. We have to use the combination of multiple of 2 and multiple of 3 to take care of either even or odd. So that we'll see later. But first let us see that what this 3/8 rule is about. So in 3/8 rule, what we do is that unlike Simpsons 1/3, in Simpsons 1/3 we were fitting a polynomial through 3 points. Here we are fitting a polynomial through 4 points. So you can see that in 3/8 rule, the red polynomial is going through x0, y0, x1, y1, x2, y2, and x3, y3. Therefore, the equation of this red polynomial, that should be y equals this li yi, that grows from 0 to 3. These L's are Lagrange polynomial. That means y is given by L0 y0 plus L1 y1 plus L2 y2 plus L3 y3, and we know that Li, this is the standard expression for Lagrange polynomial. It will start from j equals 0, it will go all the way up to 3, but j will not take I for Li. This is x minus xj, xi minus xj, product of all of this. That gives us this Lagrange polynomial. So in this case, we are taking uniform step size or uniform grid, which means this xi plus 1 minus xi, that is constant, and that is the step size h for I equals 0, 1, 2. That means x1 minus x0 is h, x2 minus x1 is also h, x3 minus x2 is h. Alright then, it should help us to simplify this expression. This xi minus xj, I can put it in some form of h here. So the top part doesn't do anything. This is simply the product of x minus xj, but in bottom, each of this term will bring some h, so there will be a cube of h because 3 terms will be multiplied. So there will be a cube of h with some constant will come here. And we'll see what that constant is. That would be different for this different Li. And then once I have this Li's, all I have to do is that I have to take this y and I have to integrate this y naught, y1, y2, y3. These are constants. So integration of this y basically means that integration of this Lagrange polynomial. And we will see how we can do that. So in case of Li, if I integrate over x0 to x3 for this Li, this bi is a constant h cube, it will come out, and we have to do an integration of x0 to x3, j equals 0 to 3, x minus xj dx. So for example, L0 dx, in L0, this I equals 0, so j cannot be I, so I have x minus x1, x minus x2, x minus x3 at the top. At the bottom, I have x0 minus x1, x0 minus x2, and x0 minus x3. Now x0 minus x1 is minus h, x0 minus x2 is minus twice h, x0 minus x3 is minus 3 times h. So together it will give me minus 6 times h cube. So this b naught will be minus 6. It is a constant. This b naught will be different for L1 or L2, but always it will be a constant. So I can take this b naught h cube left side and I can write b naught h cube is x0 to x3 L naught dx, which is equal to the integration of x0 to x3, x minus x1, x minus x2, x minus x3. We can evaluate this integral, and that would be it. Once we evaluate, we should be able to evaluate integral of y. The b naught, by the way, you can do the calculation just like this. I am not going through every detail, but for L1 you will find b naught will be 2. For L2 again b naught will be minus 2, and for L3 b naught will be 6. You can take an idea that what will come for instance for L3. So for L3 it will come this x3 minus x0, x3 minus x1, and x3 minus x2. This 3 will come at the bottom here. Therefore x3 minus x0, that would be 3 times h, x3 minus x1, that would be 2 times h, and x3 minus x2 will be h. Together it will give 6h cube. That is why this b3 is 6. Similarly, you can try finding b1 and b2. So these are trivial exercise. The important part is the evaluation of this integral, and this is important because integration of Lagrange polynomial is slightly complex. So let us see how can we evaluate this integral. So this is our integral. I have removed the limit here. First just evaluate the integral and then we'll put the limits. We'll use the generalized form of integration by parts. If I have two functions u and v, both are functions of x, and I want to integrate with respect to x like this, then integration by parts, we pick one, this one u that we have put out, and the v is the integration with respect to x, then generalized formula of integration by power is that this u I'll keep on differentiating and v I'll keep on integrating, and eventually it will create a series, and that series must converge. If it doesn't converge, then we have to look for something else. So what we do, we pick u in such a manner that after few derivatives, this derivative of u will become 0. Then subsequent all derivatives of u will become 0. So that is how we do it. So let us see that how we do it in this case. So for example, to evaluate this integral, I pick this u as the first two terms. This is completely arbitrary, and you can pick another u. There is no problem. So in this case, there is no problem. So this is x minus x1 into x minus x2 is my u, and my v is x minus x3. So I differentiate here and I integrate the other function. This v function I integrate. So first derivative will give me x minus x1 plus x minus x2. Then second derivative will give me 2, and third derivative will give me 0. So this is my u prime, this is u double prime, and this is u triple prime. Subsequent all derivatives will be 0, so there is no need to evaluate them. Here these are integrals of v, so this is v dx, this is double integral v dx, this is triple integral v dx, etc., etc. So the integral will not vanish, but derivative will vanish. We have to pick the function u in such a manner that derivative should vanish after few steps, then only we can use it. So now u into v dx, this is my u into v dx. So I multiply this, then I multiply this, then I multiply this, and that is how I evaluate this integral. So the first term will be this one multiplied with this one. So this is my first term, x minus x1, x minus x2, x minus x3 now square, because here I have square, divided by 2. The second term will be this, but there will be a negative sign here. So this is my second term, x minus x1 plus x minus x2 multiplied by x minus x3 cube divided by 2 into 3, that is 6. And third term will be 2 multiplied by this, so 2 cancels, 3 into 4, 12. So this is x minus x3 to the power 4 by 12. And then there is a constant of integration. It really doesn't matter here. So this is our integral. Now we can actually take the limit. We know that b naught h cube x naught to x3 L naught dx is the x naught to x3 limit of this particular integral. So if I put the limit here, you can see that each of them has an x minus x3 here. So for x equal to x3, if I put, this will be 0, this will be 0, this will be 0. C really doesn't matter here. C will be cancelled anyway. So for x equal to x3, this is 0. But x equal to x naught, it is obviously non-zero. And that's what we have to look into. So here I'll put, in place of x, I'll put x naught in all these three. So in the first term, I'll put x naught here, x naught here, x naught here. And it will be negative because this is on this side. I'll take first the x3 and then I first take the minus of x naught. So this will be negative. And then the second term again, in place of x, I'll put x naught. So this is x naught minus x1, x naught minus x2, and x naught minus x3. Here it was already negative, so it will come down to be positive. The third term, x minus x3, so it is again negative, and this is x naught minus x3. Now what we'll do, each of this we'll write in terms of h. So x naught minus x1 should be negative of h, because x1 minus x naught is h. Similarly, x0 minus x2 is negative 2h, x0 minus x3 is negative 3h. Similarly here, x0 minus x1 is negative h, x0 minus x2 is negative twice h, and x0 minus x3 is negative 3h. Here again x0 minus x3 negative 3h. So this is an expression of h. We can simplify it. If you simplify, you will get negative 9 by 4 h to the power 4. Therefore, this b0 h cube integration L0 dx is minus 9 by 4 h to the power 4. That gives us this L0 dx integration x0 to x3 is minus 9 by h 4 b0. So in general, we can carry out this kind of integration for all these L's, and what you will see that all of them will come down to this 9 by 4 h to the power 4. Either they will be plus or they will be minus. However, these b's are different. b1, b2, b3, they are all different. They are different from b0. So it will come at 9h by 4 bi, whatever the b for that li. And some of them will be negative, some of them will be positive. L0 is negative, and again L2 will be negative. So this is minus 1, I plus 1, L0 I is 0. So this is minus here. For L2, this would be simply 1. And L3, again it will be negative, etc. So now we are ready to evaluate the integral. So here I had this expression y equals L0 y0, L1 y1, L2 y2, L3 y3, and we have just seen that Li dx is minus 1 to the power I plus 1, 9h by 4 bi. Although I have not derived it for all I, but I have derived it for L0. You can try yourself the derivation for other i's. These b values are b0 is minus 6, b2 is minus 2, b1 is 2, and b3 is 6. So now we are ready to plug this here in this expression, that is integral of y dx. You can see that y0, y1, y2, etc. they are all constants, so they are out of the integral. And L0 dx, L1 dx, etc. we have evaluated is here. All of them contain 9 by 4 h. So together, if I plug them in, this will come as 9h by 4, because all of them contain 9h by 4. Negative y0 by b0 plus y1 b1 minus y2 by b2 plus y3 by b3. I can now plug the values of these b's, and once I do it, the 6 will come. I multiply with 6 and I get this expression. This is the expression of Simpsons 3/8, 3h by 8, y0, 3y1, 3y2 plus y3. You can now understand why you call this 3/8 rule, because of this 3/8 that is appearing at the beginning of the expression. Now I can frame the composite Simpsons 3/8 rule for n number of points, or n number of intervals rather. That would be 3/8 by 8. It will go y0, 3y1, 3y2, this y3 next segment will come and it will make this y3 twice. This is how it will go 1, 3, 3, 2, 3, 3, 2, 3, 3, 2, etc. And again it will end as 1. So you can see that it always requires 3 segment here. You can see that it requires 3 interval here. Then again in next segment it requires 3 interval. Then again in next segment it requires 3 intervals, etc. So it requires a multiple of 3 intervals. If it is not a multiple of 3 intervals, it will not work. So that is the problem here. So if we do the error analysis, which I have not done here, but you can look into your textbook, you will see that these rules have the same order of accuracy. Although value-wise 3/8 is slightly more accurate, but the order of accuracy is same. Now, same order of accuracy, so if I use them together, it will not reduce the order of accuracy. Just like if I use Simpsons and trapezoidal together, the order of accuracy will come down to order of accuracy of trapezoidal, which is less than that of Simpson. But here I can use them together. That is the good thing about it. So what we do in reality is that if I want to keep the higher order intact, I use a combination of 3/8 and 1/3. N is either a multiple of 3 or not a multiple of 2 when it happens, then we use a combination. So for example, if N is a multiple of 3, so let us say this is 9, then I can go for 3/8 rule. If N is 8, I can go for 1/3 rule. But it's, let's say N is 7, I cannot use any of them individually, but I can use them together. So for example, I can have this 7, I can break it down to 4 plus 3 intervals. In these 4 intervals, I use Simpson's 1/3, and in this 3 interval, I use 3/8. That is how any integer n can be broken like this, as a multiple of 2 plus a multiple of 3, that way. And that way, we can have this high order of accuracy, this globally 4th order, locally 5th order accuracy. I can keep all throughout, which was not possible with a combination of Simpson and trapezoidal. As a summary, we have seen a technique where we are using a higher order Lagrange polynomial. Here we are using up to 3, but now you know the technique. So if you want to use even further, you know how to derive such technique. Depending upon your application, you can derive higher and higher order polynomial based integration. For your exercise, you calculate both analytically and numerically using all these 3 methods that you have learned. This integral 0 to 1 root over 1 minus x square dx. If you can do a computer program, then you can write the program for this. If you cannot, then what you do is that you take few segments and calculate manually. That's all for this lecture. Thank you, and I'll see you in next class.